In example 2.1d, we'll be looking at the equation y equals x cubed. So the operation here is an exponent of 3. So we should be familiar with what that does. And the name for this is the cubic function. And we can define that. We'll call it f. And just like with the squaring function, you can take any real number you want and you can raise it to the third power. There's no restrictions on real numbers with doing that. So we'll make the domain all real numbers. The second set will always be all real numbers given by f of x is equal to x cubed. We'll make our table, and our table will begin just like all the others have preceding this. It's one of those things, when it's not broke, don't fix it. These x values work great. Now, because we have an odd power, power of 3, the negative entries are going to end up being negative on the output side of it as well. So -2 is going to map to -8, -1 to -1, 0 to 0, 1 to 1, and 2 will map to 8. So you just have to take your x value, put it through the operation, and you get your points. So we'll see a little similarity to the quadratic function, but there'll also be a major difference. So let's plot these points, starting with 0, 0. So one of the similarities here is that you can see the point 0, 0, and 1, 1 are the same as what you'd get with the quadratic. But your second or third point, I suppose, the one that goes with an x value of 2, ends up going all the way up here to 8. So it's almost like a stretched out version of what you would get with the quadratic. But on the left side of the origin, where you would have the negative x values, it's not going to be a mirror image. It ends up being a different type of symmetry. Again, we'll talk about this later on, but you get something that ends up in the third quadrant instead of in the second quadrant. I'm having a tough time with the graph here. Let's try that again. There we go. That looks much nicer. And it looks something like this. So this is the cubic function.